All right, the next talk will be a conceptual framework for safe object initialization by Clément Blaudeau and Fengyun Liu. Clément?
All right, thank you. Thank you all for being here. So my name is Clément Blaudeau. I'm a third-year PhD student at INRIA, and I'm going to present a work we did with Fengyun while we were at EPFL. So the goal of this work is to provide you with a conceptual framework. So I'm going to detail a bit what this means for safe object initializations. So what's the deal with object initialization? Let's look at a couple of examples. Let's say you're tempted to write this kind of code where you have several fields, and the examples will be given in Scala throughout the presentation. And here you try to access a field before it's initialized. So you get an initialization error. You have a field access that's too early, basically. Another variant of that error is to try to call a method on the object, on the this object, before the object is initialized, and again, you reach the field before it's initialized through a method called, and so you have a method code that's too early. And another way of having the same kind of issues is that if you build your object and inside the constructor of your object, you pass the this pointer to another object. And so the B class here expects an A object, so it tries to access a field of A, and there is an initialization error. And the third one is more worrying because it means that the error can appear anywhere in the program. Actually, the core problem of initialization is that objects under initialization that do not fulfill their class specification yet. And so this is a big deal because it means that when you have objects that are not fully initialized, they break the core assumption of object-oriented programming that objects that do fulfill a class specification, it's not the case. Okay, so you may be tempted to say, okay, let's forbid all of this crazy code inside the constructor. But the thing is, there are examples where you actually want complex initializations, where you're happy to be able to have escaping of the this pointer before the end of the initialization, so you can have cyclic structures. And here you can verify that there is no early access in this code. Another example is maybe if the initialization process is very long, you have some server and the initialization process takes a long time, and you want to emit some effects before the end of initialization. And maybe that's safe to do so if you can start broadcasting even if the rest of the server is not ready or something. Okay, so here we have kind of the examples of things can go wrong and things can go right, and how can we find a sweet spot in between. So we have a design space. Okay, we want to prevent all initialization errors. Okay, so we want a sound system in which it's impossible to access a field before it's initialized. But this is kind of a large design space. It goes from very strict initialization, where you're not allowed to use the this pointer before the end of the constructor, like you have in the OCaml objects, for example, all the way to full separation logic proof of program, where you're allowed to do anything. Inside this design space, we're interested in having an expressive system in which you're allowed to do some form of controlled escaping to build up those cyclic structures. But at the same time, we want a system that's modular, which means that we want a class-by-class analysis, and if possible, we want a limited footprint, which means that if the code does not do crazy initialization stuff, the initialization checks should not invade all of the rest of the code. It should be of limited footprint. And so the last thing we want in the design space, design requirements for a system, is for it to be usable, which means that it should be understandable by the user and, if possible, inferred in most common use cases. So that's where we believe that Celsius stands, some sweet spot inside this design space, and that's what I'm going to present now. So in this presentation, I'm going to give you an overview of the Celsius model, so how we represent object under initialization, and then I'm going to present the core principles, the main idea behind the design choices of Celsius. And those core principles are high-level design ideas that you can apply to your language in very different ways. And I'm going to illustrate one way of applying it to a minimal calculus that we give in the paper to show that actually it works to have those principles. And if you follow the principles, you'll be rewarded by the local reasoning, which is kind of the core idea of the core property of a system for safe initialization that I'm going to give you an overview of. In the paper, you'll find the actual calculus that illustrates those properties, the typing system with temperature annotations that you have for your that we have for the minimal calculus. And then a soundness proof that is very modular because it only relies on the principles in a way. And also everything is implemented in Scala, so Scala is way bigger than the minimal calculus, but the ideas are kind of the same, and everything is proven in Coq. Okay, so let's jump in the Celsius model. So how do we model object under initialization? So the idea is that when you start at the beginning of the constructor, the object has no initialized fields. Okay, so we consider it cold. A cold object, you cannot access any of the field of a cold object because they might not be initialized. And then throughout the constructor, some field will get initialized and the object will get cool. Once you've reached the end of the constructor, hopefully you've initialized all the fields and you get a warm object. And the thing is, a warm object is not ready yet. It does not fulfill its class specification yet because it might still have inside one of its fields a cold object. So using a warm object might still be unsafe because you might still transitively access an uninitialized field. So initialization is really finished when you have hot object and you can only reach transitively objects that are freely initialized. Okay, so that's it for the Celsius model. Now let's talk a bit about the core principles that support the Celsius model. And again, those are design principles, and you can apply them in many ways to your language. The first principle is monotonicity. We believe that that's a good idea when you have evolving states that they evolve in a monotonic way. So the initialization states should also be like the arrow of time, in a way. You can enforce several granularity of monotonicity. One is partial monotonicity, when you disallow the uninitialization of fields. But for soundness, we need a stronger notion which is called perfect monotonicity. Because if you disallow the uninitialization, it will prevent warm object from getting cooler, but you can still have an hot object that gets warm because you put a cold object inside one of its fields without deinitializing it. And in the calculus, we implemented monotonicity with language design. We don't have a way of deinitializing a field, so we don't have like null values, those kind of things. And we also have a typing restriction that you can only update fields with hot values. But again, you can enforce the principles in many ways. As the second principle, which is very linked to the notion of monotonicity, is called authority. If you have two aliases of the same object and you do an update on one of the alias, you can maybe consider it to be hot at some point. But the local visions you have of the initialization state might differ between the different aliases. So you might do something on one of the alias that is locally monotonic, but actually globally is not. So if you do some update on the second object, and that downgrades the first. So in the presence of aliasing, to ensure monotonicity, you need this notion of authority, which means that state updates are only authorized on a distinguished alias. And a natural candidate for this distinguished alias is the this pointer, which is like a natural candidate for between all of the aliases of the object. In practice, in the minimal calculus, we only authorize the typed updates, so the object getting hotter inside the constructor. And we distinguish between first assignment, so when a field changes from uninitialized to initialized, and updates of a field. Okay, so now we know, thanks to the first two principles, that objects get hotter over time, but how do we know that they reach warm at some point, that we finish the initialization of the fields? The principle of stackability, and it states that all fields must be initialized at the end of the constructor. The intuition behind the word stackability is that the constructors, they form a cold stack. There are different ways, again, of enforcing this principle. In minimal calculus and in Scala, we have mandatory field initializers, and we do not have control effects in the constructor, so there's no way of like throwing an exception and not finishing the code of the constructor, which could like break the stackability principle. Okay, if we combine the first three principles, let's look at, so the question is, how do we get from warm to hot object? And if we combine the first three principles, let's say we have some object and we create a new one that starts cold, and the creation of that object might trigger the creation of other objects. And so we have the object gone from cold to cool, and you may have cycles, and at some point the initialization of C3 finishes, so you get a warm object. And the initialization of C2 finishes also, so you get, again, a warm object. And then you know that you only have warm object in your heap, so you know that you can only transitively reach things that are fully initialized, so you can upgrade all of the objects from warm to hot. But what happens if inside the heap there are also other objects that are unreachable and that are cold? Like what happens if you have parallel initialization or if you have nested initialization processes? In those cases, you will not be able to upgrade a set of objects from warm to hot if you don't know that they are actually in a restricted part of the heap. So the principle of stackability states that basically you should control the accessible part of the heap to show that in this accessible part of the heap, there are only warm objects. So the principle of scopability, access to object under initialization must go through controlled channels. In the calculus, we remove global variables because if you have like cold objects that are globally available, you never know that the object you're building will ever reach the hot status. But this was covered by my co-author in the paper published at OOPSLA this year and presented this morning. And also we have like in our setting we over-approximate the set of the heap that's accessible basically. Okay, so that's all the four principles, and if you manage to have all of those principles in your language, then you will get the local reasoning property, which is like kind of the core property behind our approach. And the idea is that if you execute an expression or a program inside a hot environment, so it only accesses a hot object, you will the result you will get will also be a hot object. And why is it the case? I'll show like an overview of the proof because it shows how the principles appear. The idea is that after the execution, you have a resulting heap, and you have the object that was produced. And if you try to access an object from the object that was produced, it's either a new object. So if it's a new object, it means that we run its constructor, and the constructor finished, so it's a warm object. And if it's a old object, it was already accessible in the heap from the execution environment before. And before the execution, it was hot, because the execution environment was hot. And thanks to, let's advance a bit. So the old object was already accessible by the scopability principle. And as it was hot before the execution, it remained hot thanks to monotonicity and authority. So in both cases, you can only access warm or hot objects, so it means that actually you can only access things that are fully initialized. So the object you get is fully initialized. And this gives rise to a typing system where you have hot bypasses, meaning that when you know the piece of code you're considering is not doing crazy initialization stuff because it's only in a fully initialized context, you can ignore these initialization checks when you handle like hot objects. So let's quickly take a look at how it applies in a like modified scala with temperature annotations, which is the minimal calculus basically. So I revisit the example before, and I add annotations to all the types in the fields of the objects. And you can check that basically you have like the obligations, and you never access an object that if you don't have the corresponding temperature. And the thing is that if you have another part of the program that does not do crazy initialization where you need to finally check that all the fields are well defined, like for example in the main class, you know that the initialization starts in a hot environment, an empty environment, so it's hot. And you know that at the end you get a hot object. So in the rest of the program here, you can completely ignore initialization checks. So that's really the beauty of the local reasoning principle. So it does not like pollute the whole of the program. When you handle hot objects, you can just ignore the initializations. Okay, so what's the takeaway? So I gave you like a kind of a conceptual framework for self-initialization, meaning that it's a simple interface to a solved problem. You can think of the initialization problem in terms of the four principles, and that gives you a good overview of what's going on. You have the Celsius model for initialization of objects. You have the 4 language agnostic principles that you can, again, enforce in many ways, and the core idea of local reasoning. And I invite you to see the paper for the precise definitions, the typing system, the soundness proof, which again is modular in the sense of the principles. It's quite interesting. And some hints on the Scala implementation. Thank you very much for your attention.
All right, great. Do we have some questions? I'll start with one while people are coming up. Is this shipping with a Scala compiler? Is there conversations about like putting it into practice?
That's a very good question. It's actually right now in the Scala free compiler. You have a compiler option to activate the initialization check. Same as for the work on global objects. You have an initialization check. And the implementation like kind of follows the principle, but the language is way more complex. So there are a lot of other things in the actual implementation. But yeah, it's currently in Scala.
Yeah, excellent.
I'm not quite sure if I got completely the way it's working. What's about the constructors? So as long as the constructor is not completed, you may still have critical initialization steps going on. In the examples, you showed the direct initializations of variables, so I'm not quite sure how the effect of constructors is modeled in there.
So let's go back to this example in the Celsius syntax. So the way we model this problem, and it's the same in Scala, we have mandatory field initializer. So the constructor, you should think of it as like the list of those expressions on the right that are the basic initialization for those fields. But you can also have like a normal constructor, which is a function, and it can do anything. And then we said that you should prove in some way to have the stackability principle that at the end of the constructor or at the end of the initialization process, you have initialized all the fields. Does that answer your question?
Yeah, okay, and then I think I get it. Yeah.
Sorry, so the design aspect here is that we have a basic initialization value for all the fields. So we know at least that there is something inside all the fields at the end of the initialization.
And then maybe a comment more. These terms, hot, cold, cool, confuse me a bit because hot is dangerous, soft, whereas cool is, let's say, stable, safe. Yeah? So it's counterintuitive in that context for me. Did you pick them from somewhere else? Did they exist already, or was it your?
It's more of a cooking idea. So you cook the object, and at some point it's fully cooked and it's ready to hit. But actually, we discovered like yesterday that it's also a terminology that is used in some distributed systems, like when you have like a VM that starts and it's not ready yet, it's cold. And it like ramp up to being hot and usable. So it is accidentally a terminology that is used elsewhere, but yeah, the intuition more comes from like a cooking.
Thanks.
Thank you.
All right, one more question. Yes.
I have one question. So, am I correct that, like, if you don't consider the mutually recursive initialization, then you can just topologically sort and then initialize from the left, and the problem becomes easy. But in the actual Discord, there is a mutually recursive initialization going on, and the type system you have devised is basically ruling out like the cycles, like the meaningful cycles that actually access the field of the object. But the type system you devised ensures that such a cycle doesn't happen. Is my understanding correct? So
you can have cycles, like you can realize the object that the this pointer, for example.
Okay.
But there are some patterns that you cannot do with this system, definitely. But like basic cycles where you do an alias of yourself or those kind of the patterns are allowed. But you cannot access a field of yourself while you're initializing.
Yeah, thank you.
Thank you.
Thank you. So you told us about this problem of initialization in the context of Scala and objects. Are there other languages or language features where a similar problem would show up?
So that's a very good question, and actually it's kind of ongoing research, just started. But yeah, the module system of OCaml has recursive modules, and they have an initialization phase that is not well documented and also kind of broken. There are like dynamic checks and everything, and we would like to apply this approach to this system. So definitely, I think there are more languages that could benefit from this approach. Thank you.
All right, thank you so much.
Thank you.